Hi, welcome to our Tech Talk. I want to talk a little bit about active heat transfer devices in the Melvin and Sefton motors. If I look at a heat engine, right, the whole thing about the heat engine is getting the heat into it and getting the heat out of it, right? That's how it works. That's the whole key of it. If I look at how that happens on most Stirling engines, I have a cylinder, and inside that is a working gas, could be air or something else, and then the surface area of the cylinder which surrounds that volume. The volume of the enclosed space is heated and cooled by this surface area. Right? So surface area is the key to the heat transfer. Now what's interesting is, as the size of that cylinder changes, say I have a cylinder that's 1x1, small one, 2x2, or 3x3, the largest one, interesting thing happens. We see that there's a change in the ratio between the surface area and the volume. You say, well, why does this matter? Well, if the surface area is what's heating and cooling the gas, and the ratio is less surface area per unit volume, as the cylinder gets bigger, well, that means a less efficient engine. So, interesting thing here is the area, as it gets bigger, the area grows as a square of the size, right? Square inches, square foot, right? The volume grows as a cube of the size. So as it gets bigger, the volume quickly outpaces the surface area as a ratio between the two. Now, you might say, well, why is this important for Stirling engine efficiency? Well, most Stirlings today are pretty small, because a smaller sized engine provides for a more efficient system. We're working with active heat transfer devices to change that paradigm, and here's how. We've introduced what we call an active heat transfer device into our engine. And these active heat transfer devices take up almost no space and yet reach into the most difficult areas to help heat the air when it's going through the heating and cooling cycles. So if I look at it, this is a diagram of it. It's kind of like a conical spring. You can think of it like that. And when the displacer is all the way at the end, it's flat. And when the displacer goes in the other direction, allowing the air to flow into the void, the element expands and starts to heat that working gas. Here you can see some examples of the heating elements during development. It's paper phase and then another prototype. And finally, this is what you'll see in the Melvin on the right side. The element's made of hardened stainless so it does not deteriorate in the heated condition or lose its spring at operating temperatures. And we find that spring does help with the reciprocating mass of the displacer. But the active heat transfer device is on both ends of the engine, so it helps with the heating and the cooling. Here you see the displacer as it travels first during heating, back, expands that active heat transfer device, helps to heat that volume of air, and then during cooling, goes the other way. The heated active heat transfer device is actually being recharged in its flattened state against the hot wall, and then during cooling, it is expanded out and helps to cool that particular air. And this is our heat transfer device in the Melvin engine at Sefton Motors. By utilizing this, we can easily increase the size of the bore of the engine and still maintain a high level of efficiency. This allows us to get to a larger, more powerful, and lower cost engine. And that about does it for our Tech Talk. Thanks for watching.